Welcome to our second lesson on Unit 1 on analyzing graphs of relations and functions. In this lesson, we will be focusing on using graphs to find the domain, the range, the intercepts, the zeros, and the values of functions. We will also be learning to identify odd and even functions by looking at the graph. To begin, let's start with a review of some common vocabulary on functions. The domain are the x values of a function or the inputs. The range then are the outputs or y values. An intercept is where a graph crosses either an x or a y axis. And remember, when we find an intercept, the opposite variable is equal to 0. So you can see in this function here, the x-intercepts have y coordinates of 0, whereas the y-intercept has an x-coordinate of 0. When we talk about the zero of a function, we are actually just asking to find the x-intercept, where it crosses the x-axis. Let's start with some examples. Our directions say to use the graph of the function to find the domain and range of the function and approximate its y-intercept and zeros, if there are any. Then we're going to find those values algebraically. So let's go ahead and jump in. So if we want to just use the graph to find the domain and the range of the function, when we look at this function, what values of x are we allowed to use? Are there any x values that are excluded from the domain? And it looks like if you run along the x-axis, we have all real numbers, okay? So we could just say all reals for the domain. Then when we look at the y values, or the range, what kind of outputs are we going to get? Well, the y values, we have a minimum point down here of -16. We can see that as the y coordinate of the point. And so the y values, the smallest value we will get for y is -16, but we will have a lot more y values after that on to infinity, because we have y values all along this. Because of these arrows, any point on this graph, we're going to have y values all the way to positive infinity. But the smallest y value is at that point right there, and that point is -16. So our range would be anything from -16 to infinity. Our domain, if we wanted to write that in interval notation, would be from -infinity to positive infinity, because it's all real numbers. So there's our domain and our range. Now the y-intercept and the zeros, let's take a look at those. The y-intercept is where it crosses the y-axis. And so if we look at our graph, the y-intercept crosses right here. And that value looks to be like -12. So from the graph, we're going to say the y-intercept, we're going to say that is -12. Okay? So that would actually be the point x is 0, y is -12. And then the zeros, remember the zeros are just where it crosses the x-axis. So the zeros, we have 2 of them, and I have those in green. The zeros look like they are at the points, let's see, we're going by 2, so it looks like -2, 0, and we have one more on the right, and that one looks like 6, 0. Now those are just using the graph. We also want to find those algebraically, so let's go ahead and do that. So to find, first of all, to find the y-intercept algebraically, so the y-intercept is found when we let x equal 0. Remember, the opposite variable is 0. So in our equation right here, I am going to let the x value be 0. So we will get g of 0 would equal 0 squared minus 4 times 0 minus 12, which is 0 minus 0 minus 12, which is -12. So this, we verified, is our y-intercept. So what about the actual zeros or the x-intercepts? Let's verify these two values algebraically as well. Well, in order to find those, notice our y-coordinate is 0, so we're going to actually let the y-coordinate or the output be 0. So we would get 0 equals x squared minus 4x minus 12. So now we need to figure out how to find the x values when y is 0. Well, hopefully you remember a little bit of factoring from your advanced algebra course, where we factor the first terms come from x squared. Then we want factors of 12 that differ by 4. And we know those to be 6 and 2. Our signs on our factors are going to be different because that's a minus, and the bigger factor will be minus. So that tells us that the bigger factor of 6 is minus, and this one is a plus. And now remember, we set each factor equal to 0 and solve. So we get x equals negative 2, and then x minus 6 is 0 gives us x equals 6. So our x-intercepts are negative 2 and positive 6. And that is what we had graphically as well. Here's another example using the graph to do the exact same thing. Well, let's look at the domain of the function. Our domain of this function, it looks like we could have all reals again. Okay, so we're going to go from negative infinity to infinity. Another way of writing that, you could just say all reals or just use the capital R. The range of the function, well, are there any y values we're not going to get? And again, this one is all real values, all real numbers from negative infinity to infinity. So the domain and the range on this one are both all real numbers. Well, what about the y-intercept? How do we find the y-intercept? Well, our y-intercept, it looks like it crosses the y-axis only one time right there, and it looks like the y-intercept equals 0. And the way that we would find that is by letting x be 0 in our equation. So we want to find f of 0 in our equation, and that would be 0 to the third minus 0, right? We're just substituting in a 0 everywhere into our equation where x is found. We're putting in a 0. So indeed, we do find that is equal to 0. So we verified that algebraically. So now let's go ahead and look at what our x-intercepts or our zeros are. So let's find the zeros, and then we'll verify those algebraically as well. I'm going to erase a little bit of this so we're not getting too confused here. So let's take a look at that. I'm going to pick a different color that we're looking at where these values, where it hits the x-axis. It looks like there's 3 of them. And so from the graph, our zeros look like they occur at, and we don't have units on here, so I'm going to guess these are one unit at a time. It looks like it's at negative 1, 0, and then it looks like there's another one at positive 1. So we need to find those algebraically now. So let's go ahead and do that. So if we have f of x is equal to x cubed minus x, we want to find out where that thing is equal to 0. Well, this thing we can factor out an x from both terms. And when we do that, we're left with x squared minus 1. Well, now set each factor equal to 0. So the first one is x equal to 0 when we set this one equal to 0. When we set x squared minus 1 equal to 0, we get x squared equal 1 when we add 1 to both sides. And then taking the square root of both sides, we get x is equal to plus and minus 1. So indeed, when we solve this algebraically, we got 3 solutions. We get x equals 0, x equals 1, and x equals negative 1. Sometimes graphs have symmetry properties. And so we're going to be looking now at some properties of symmetry with our graphs. And there are 2 different kinds of symmetry we're going to talk about. The first one is line symmetry. And line symmetry occurs when a graph can be folded along a line and the 2 halves match exactly. Another kind of symmetry is point symmetry, when we can rotate 180 degrees and it looks the same. Okay, so let's take a look at the graphical and algebraic tests for these kinds of symmetry. And there's also a model for you to look at. So we have symmetry with respect to the x-axis only if the point x negative or xy results in x negative y for every single point on the graph. Then that gives us symmetry about the x-axis. So you can see if you have a point here, it's reflected about that x-axis and we get x negative y. To find it algebraically, we replace y with negative y. The second kind of symmetry is respect to the y-axis. We find that when every point xy results in the point negative xy, and again, replace the opposite variable with negative x. So it's symmetric about the y-axis if we get the opposite x value. It's kind of the opposites. You'll notice that they're the opposites. With x-axis symmetry, we get opposite y's. With y-axis symmetry, we get opposite x's. Then we have a third one. The graph of a relation is symmetric with respect to the origin if every point xy on the graph, the point negative x negative y is also on the graph. So that one we replace x with negative x and y with negative y, and that gives us symmetry about the origin. So let's take a look at some symmetry examples. It says use the graph of the equation to test for symmetry with respect to the xy axes and also the origin, and then confirm that algebraically. Well, this one looks like it's symmetric about the x-axis. So the way we would test that, and I need to reveal this for you, symmetric about the x-axis, we would test that by checking to see if we put in a negative y to see if we get that point. For every point xy, we want to end up with an x negative y. So the algebraic test, because when we put in a negative y, we end up with the same equation. So in our original equation right up here, we're going to substitute the value negative y in there, and that ends up being the same thing. So negative y squared turns out to be a positive y squared, which gives us the same equation. So that's how we prove that it is symmetric with respect to the x-axis. On letter B, the graph looks like it's symmetric about the origin here. It looks like if we just rotate that 180 degrees, we'll get it. So we're going to test for that algebraically by putting in a negative x and a negative y into our original equation and seeing if we get the same equation. So if I put in a negative x here and a negative y there, we're going to substitute that in. Those negatives cancel out and give me positive xy. That's the same equation we started with, so it's symmetric about the origin. Odd and even functions. Functions that are symmetric with respect to the y-axis are called even functions. For every x in the domain, f of negative x gives us f of x. So when we plug in a negative x algebraically and we get the exact same function that we started with, we know that it's an even function. An odd function is when we substitute in that same negative x, but we get the function with a negative 1 multiplied by it. So that's how we're going to test for oddness or evenness of functions. So let's jump in and look at some examples there. And let's start off with number 1. We're going to plug in f of negative x. That's what we use for all of these. And then we're going to compare it to what we started with. So f of negative x is equal to, we have 2 over whatever x is squared. And remember, we're plugging in negative x. And then we want to evaluate that. Well, what is negative x squared? Well, negative x squared is negative x times negative x, which is just positive x squared. So these two are exactly the same. So that's a situation where we ended up with the exact same thing we set up here. That's the same as our original function. So this one is even. So let's look at letter B. We're plugging in g of negative x. And is that the exact same thing? Well, this one is not the same thing, and it's also not negative f of x. So this one is called neither. And the last one, letter C, when we plug in negative x, h of negative x is equal to negative x to the 5th minus 2 times negative x to the third plus negative x. Well, remember, a negative number to a negative exponent is negative the thing to that power. So then the next term is negative 2 times negative x cubed. And that one, this negative x to the third is negative outside. So we'll end up with negative x to the fifth plus 2x cubed. And then this last one then is minus x. So that's what we end up with. So now let's see what this one would be. If we took this function times negative 1, what would we get? Well, I would get negative x to the fifth plus 2x cubed minus x, right? If we distribute a negative 1 through that parenthesis, and then let's compare that. Is it the same thing? And it is. So that's the situation we had where it was an odd function, so we're going to say that one is odd. So odd, even, or neither. Here are a couple of problems for you to practice on your own and bring to class, and we will talk about those in class next time. Thanks for listening.